Section 2.7 is square roots and real numbers. So let's take a look at square roots. A square root is one of two equal factors of a number. So in other words, if we can take a number and find two factors that are the same, that's the square root of the number. So the square root of 64. Well, the factor that I can multiply to get 64 where the factor is the same is 8 times 8. So the square root of 64 is 8. However, let's keep in mind that if we multiply negative 8, so 8 is one of my square roots, because 8 times 8, but negative 8 is also a square root, because negative 8 times negative 8 is 64. So every value has two square roots. Any number whose square root is a rational number is a perfect square. In other words, if the values that we get for the square root can be written as a rational number, then we call this a perfect square. 64 is a perfect square. Let's make a list of some of the perfect squares. 1 is a perfect square because its square root is 1 times 1. 4 is a perfect square because its square root is 2. If I square 3, I get 9, so 9 is a perfect square. 16, whose square root is 4. 25, square root is 5. What number has a square root of 6? 36. Square root of 7, 49 is square root of 49 is 7. The square root of 64 is 8. And see what I'm doing? All the perfect squares, or the squares of our integers, working my way up. The square of 9 is 81, then 100, then 121, whose square root is 11. 144, whose square root is 12. 169, whose square root is 13. 196, whose square root is 14. And 225, whose square root is 15. And I would like you to know this, all the perfect square numbers through 225. So this is a list of perfect squares that you should be familiar with. Okay, so this symbol is called a radical symbol or a radical sign and is used to indicate a square root. So the square root of 16 equals 4 indicates the principal square root. If we don't have a symbol in front of the square root, we generally are saying that we're looking for the principal or the positive square root, and we're just going to write 4. The negative square root of 25 is negative 5, and this is called the negative square root. So we have the principal square root, which is positive, the negative square root, which is negative, and then if we have this symbol, which is read plus or minus, it indicates that we want both of the square roots of 64, so we're going to say plus or minus 8. It's just a short way of writing both of them. Instead of writing both answers down side by side, it's kind of a little shortcut to say, yeah, that's both of them. Okay, so the radical symbol and the symbol for plus or minus. All right, so let's do a couple. What is the negative square root of 0.81? Well, I know that the negative square root of 81 is 9. 9 times 9 is 81. So it's going to be 9, but where do I put the decimal point? Well, let's think about it. When I square 9, I get 81. If I square 0.9, when I multiply that out by our rule of multiplying decimals, 9 times 9 is 81, and the decimal point goes 2 places, and that will get us our 0.81. They asked for the negative square root, so I put my negative sign in. How about something like this? Plus or minus the square root of 64 divided by 121. Well, I can do this as two separate pieces. I can say plus or minus the square root of 64 over the square root of 121, which is plus or minus 8 over 11, or 8/11ths. Okay, so there's a couple examples of some tougher ones. All right, we're also going to, in this section, classify and order numbers. So classify. Rational numbers can be expressed in the form a over b. They are terminating or repeating decimals. Terminating means they stop, something like 0.27, because I can write that as 27/100ths. Or repeating decimals, like 0.333 repeating, because those can be written as fractions also. And also rational are the square roots of perfect squares, and we've seen that. The square root of 16 is 4. The negative square root of 81 is 9. So a perfect square root, the square root of a perfect square, gives us an integer which is rational. Irrational, non-terminating, non-repeating decimals. So 0.2714638914 ... There's no pattern, there's no repeating, it goes on and on forever. There are a few of these irrational numbers that we use commonly. One of them is pi. We all know that pi goes on and on forever and ever and ever. And the square roots of everything that is not a perfect square. So the square root of 3 gives you a non-terminating, non-repeating decimal. The square root of 7, the square root of 4.2. Any square root, as long as it's not the square root of a perfect square, is irrational. All right, so let's do a quick Venn diagram. At the heading, we're going to have all of our real numbers. And we're going to divide this into two sections. One is going to be my rational. We'll make that one bigger because there's some subheadings there. And the other is my irrational. Now, irrational numbers like pi, the square root of 3, they don't have any other subcategories. It's just irrational. Under rational, I've got a bunch of things. The smallest category is called natural numbers. I'll put a key over here. So N is for natural numbers. We also sometimes call these counting numbers. It's 1, 2, 3, etc. If we add 0 to that, including the natural numbers plus 0, we get whole numbers. 0, 1, 2, 3. The next ring out is integers. Now we are adding our negatives, things like -3. So we added 0 to our natural numbers. 0 plus all the naturals are the whole numbers. Adding the negatives to the whole numbers gives us integers. That's -3, -1, 2, -1, 0, 1, 2, etc. in both directions. And then outside that are all of the rationals that don't fit into these, things like 3/7, 2.4. What about the square root of 64? Where would that go? Well, it would actually go under the integers because I can simplify it to an integer, plus or minus 8. So those are our categories of real numbers. We've got rationals and irrationals, and that's what we're going to be working with in this section. Okay, classify the following numbers by naming the set or sets that describe them. So 5 halves. So let's start on the inside. Is it a counting number or a natural number? No. It's not a whole number. It's not an integer. We have to get all the way up to rational numbers. And of course, everything we're going to name are called real numbers also. So it's rational and it's real. The square root of 121 is 11. So this is a counting number or a natural number. It's also a whole number. It's also an integer. It's also rational. And it's also real. Negative square root of 7 is irrational only. Oh, and real. And the last one, negative 36/9, that can be written as negative 4. So it's an integer. It's not a natural number or a whole number because it's negative. It's an integer, and it's rational, and it's real. Okay? Classifying. By adding irrational numbers, we complete the number line. If we just have a number line, if we're just doing counting numbers or integers, we have a lot of empty space in between each one. And we can fill those in with some of our rational numbers like 1/2 or 1/3. But there's spaces in between there that are not rational numbers. There's little spaces in between there. In between 3.13, in between 3.14 and 3.15 is pi, 3.14, and it keeps going. So by using irrational numbers, we now can complete our number line. And if we graph, well, let me say this first. The completeness property states that each point on the number line corresponds to exactly one real number. That's rationals and irrationals included. Graph the following. X is greater than 2. So that means that I'm going to start at 2 but not include it. So open circle. And then everything to the right, rationals and irrationals combined. X is less than or equal to negative 4.2. So 0, negative 1, negative 2, negative 3, negative 4, negative 5. So negative 4.2 and including negative 4.2. So a closed circle at negative 4.2 and everything to the left. Less than or equal to negative 4.2. And I know you've done this before. And then comparing real numbers. To compare irrational numbers, you need to use a rational approximation. So, square root of 19 and 3.8, which one is larger? Well, let's do a rational approximation. What is the square root of 19 close to? What perfect squares are close to 19? So we've got the square root of 16, which is 4. And then we've got the square root of 25, which is 5. So that I know that the square root of 19 has to be between 4 and 5. So 4 point something. We don't know what. But that's close enough because if this is larger than 4, we know that it's also larger than 3.8. Try this one. Find a rational approximation for radical 52. And then decide whether that's larger or smaller than 6.2. Okay, so I went to the square root of 49, which is 7, and then the square root of 64, which is 8. So 52 is more than 7, which certainly makes it greater than 6.2. So 6.2 is less than the square root of 52. All right, and that's it for today.